What happens if you fall into a black hole? It's a question that sparks curiosity and fear. Imagine being pulled into an abyss, never to return. This is the reality of black holes, some of the most fascinating and mysterious objects in the universe. Black holes are regions in space where gravity is incredibly strong. So strong, in fact, that nothing, not even light, can escape their pull. This makes them invisible to us, shrouded in darkness and mystery. But don't let their darkness fool you. Black holes are anything but empty. They are cosmic powerhouses, holding immense amounts of mass compressed into an incredibly small space. Join me as we journey into the heart of these celestial wonders and unravel the secrets they hold. To understand black holes, we need to talk about gravity. Gravity is one of the fundamental forces of nature, an invisible hand that shapes the universe. It pulls objects towards each other, from the smallest particles to the largest celestial bodies. Gravity is the force that pulls everything together, from the smallest atom to the largest star. It's the reason why planets orbit stars and why galaxies hold together in the vast expanse of space. It's what keeps us grounded on Earth and what governs the motion of planets around the sun. Without gravity, the universe as we know it would be a chaotic place with no structure or order. Black holes take gravity to the extreme. They are regions in space where gravity is so strong that nothing, not even light, can escape their pull. Imagine a star much bigger than our sun, reaching the end of its life. As it exhausts its nuclear fuel, it can no longer support itself against the force of gravity. It collapses under its own weight, squeezing all its mass into a single point. This process creates a black hole, a place where the laws of physics as we know them break down. This point, known as a singularity, is where gravity becomes infinitely strong. The singularity is surrounded by an invisible boundary called the event horizon. Surrounding the singularity is the event horizon. This is the point of no return, a boundary in space-time beyond which nothing can escape the black hole's gravitational pull. This is the point of no return, a boundary in space-time beyond which nothing can escape the black hole's gravitational pull. Once you cross the event horizon, there's no turning back. Once you cross the event horizon, there's no turning back. You're on a one-way trip to the singularity, where the gravitational forces are unimaginably strong. You're on a one-way trip to the singularity. Black holes come in different sizes, each with its own unique characteristics. Black holes come in different sizes. Some are only a few times more massive than our sun, while others are millions or even billions of times more massive. Stellar mass black holes are formed from the collapse of massive stars. These black holes are relatively small but incredibly dense. Supermassive black holes, on the other hand, are millions or even billions of times more massive than our sun. They are found at the centers of galaxies and play a crucial role in their formation and evolution. These behemoths lurk at the centers of galaxies, including our own Milky Way. Understanding black holes helps us unlock the mysteries of the universe and our place within it. The life cycle of a star is a fascinating story in itself. Stars are born from clouds of gas and dust, collapsing under their own gravity. As they collapse, the core of the star heats up, igniting nuclear fusion. This process releases enormous amounts of energy, causing the star to shine. For most of their lives, stars exist in a state of equilibrium. The outward pressure from nuclear fusion balances the inward pull of gravity, but this balance can't last forever. As a massive star runs out of fuel, fusion slows down, gravity takes over, causing the star to collapse rapidly. This collapse triggers a supernova, a powerful explosion that can outshine an entire galaxy. If the star is massive enough, the core will collapse further, forming a black hole. The remaining outer layers of the star are blasted into space, seeding the cosmos with heavy elements that will eventually form new stars and planets. Let's delve deeper into the concept of the event horizon, a boundary in space-time beyond which nothing can escape. Imagine it as a cosmic trapdoor, a one-way door to the unknown. Once you step through, there's no way out. It's a point of no return, where the laws of physics as we know them cease to apply. The gravitational pull inside the event horizon is so strong that even light, the fastest thing in the universe, can't escape. This immense gravity warps space and time in unimaginable ways. Think of it this way. If you shine a flashlight towards a black hole from just outside the event horizon, the light will bend towards the black hole. This bending of light is due to the intense gravitational field. But if you shine the flashlight from inside the event horizon, the light will be pulled back in, just like everything else. Nothing can escape this gravitational grip. This is why black holes appear black. They don't emit or reflect light, making them invisible against the backdrop of space. They don't emit or reflect light. Instead, they absorb everything that comes too close, including light. We can only detect them indirectly by observing their effects on nearby matter. For instance, stars orbiting an invisible point or gas and dust being pulled into an unseen vortex. The size of the event horizon depends on the mass of the black hole. Larger black holes have larger event horizons. The more massive the black hole, the larger its event horizon. This means that supermassive black holes found at the centers of galaxies have event horizons that can span millions of kilometers. For a black hole with the mass of our Sun, the event horizon would have a radius of only about 3 kilometers. This is incredibly small when you consider the vastness of space. That's smaller than a city. Yet, despite their size, black holes have a profound impact on their surroundings, shaping the very fabric of the universe. Section 5. Imagine a vacuum cleaner in space. Black holes are often compared to cosmic vacuum cleaners, sucking up everything in their path. These mysterious objects have fascinated scientists and the public alike for decades. While this analogy isn't entirely accurate, it helps to visualize the immense gravitational pull of these objects. Black holes don't actually suck things in like a vacuum cleaner. Instead, their gravity is so strong that it warps space-time around them. Imagine a large sheet stretched taut, representing space-time. This sheet is a two-dimensional analogy for the four-dimensional fabric of our universe. Now place a bowling ball in the center of the sheet. The weight of the ball causes the sheet to dip, illustrating how massive objects like stars and planets warp space-time. The bowling ball represents a massive object like a star or a black hole. The more massive the object, the greater the curvature it creates in the sheet. The sheet will curve around the bowling ball, creating a dip. This dip is a visual representation of the gravitational field created by the massive object. This curvature is what we experience as gravity. It's the reason why objects fall towards the Earth and why planets orbit stars. Smaller objects, like marbles, will roll towards the bowling ball, following the curvature of the sheet. This is similar to how planets and other celestial bodies move in the curved space-time around stars and black holes. Now replace the bowling ball with a heavier object, like a basketball. The increased mass of the basketball will cause an even greater dip in the sheet. The sheet will curve even more, creating a steeper dip. This steeper dip represents a stronger gravitational field. This is similar to what happens around a black hole. The immense mass of a black hole creates a deep gravitational well in space-time, much like the deep dip created by the basketball. Its immense mass creates a deep gravitational well in space-time. This well is so deep that not even light can escape once it gets too close, which is why black holes appear black. Anything that gets too close will be pulled in, just like marbles rolling towards the basketball. This is why black holes are often thought of as cosmic vacuum cleaners, even though they operate through gravity rather than suction. What would happen if you were to fall into a black hole? It's not a pleasant thought, but it's a question that scientists have pondered. As you approach the black hole, the gravitational pull on your feet would be much stronger than the pull on your head. This difference in gravitational force, known as tidal force, would stretch your body out in a process called, believe it or not, spaghettification. You would be stretched out like spaghetti, becoming longer and thinner as you fall towards the singularity. Of course, you wouldn't survive this process. The intense gravitational forces and radiation near a black hole would tear you apart long before you reach the singularity. While spaghettification sounds terrifying, it's important to remember that you would have to get very close to a black hole to experience it. From a safe distance, black holes pose no threat to Earth or our solar system. Black holes push the boundaries of our understanding of physics. They challenge our notions of space, time, and gravity. One of the most mind-boggling aspects of black holes is their effect on time. According to Einstein's theory of general relativity, time is not absolute. It's relative to the observer and the strength of the gravitational field. Near a black hole where gravity is incredibly strong, time slows down. This phenomenon is known as time dilation. If you were to observe a clock falling into a black hole, you would see the clock ticking slower and slower as it approached the event horizon. From the clock's perspective, however, time would be ticking normally. This means that if you could somehow survive a trip into a black hole, you would travel through time at a different rate than someone observing from a safe distance. You would essentially be traveling to the future. Black holes remain one of the most intriguing and mysterious objects in the universe. They challenge our understanding of physics and inspire us to explore the unknown. We've learned a lot about black holes in recent years thanks to advances in technology and theoretical physics, but there's still so much we don't know. What happens at the singularity? What is the fate of information that falls into a black hole? Can we harness the energy of black holes? These are just a few of the questions that keep scientists up at night. The study of black holes is a journey into the unknown, a quest to unravel the deepest secrets of the universe. From the birth of stars to the mysteries of black holes, space is full of wonders that continue to amaze and inspire us. What fascinates you the most about the vast expanse beyond our planet? Is it the search for extraterrestrial life? The possibility of time travel? The sheer scale and beauty of the cosmos? Share your thoughts and let's continue to explore the universe together.